The problem statement from GATE Physics 2010 reads as follows. In one of the following circuit, negative feedback does not operate for a negative input. Which one is it? The op amps are running from plus minus 15 volts supply. So VSAT is plus VSAT and minus VSAT are 15 minus 15 volts respectively. Four op amps are given. This is a multiple choice question with only one correct answer, and we'll try to find the correct one. And before we try to solve this problem, there are a few pre-checks we need to do. So we first need to establish whether the op amps are ideal or not. This is important because if they're ideal or very close to ideal, then we can ignore, for let's say, the input impedance and the current flowing into the op amp will be zero. So since the question is silent about their ideality, we'll simply assume that they are ideal, right? Second is the nature of feedback. The question itself says that all the four op amps are negative feedback, and you can see the output terminal is talking to the inverting terminal, so it is in all the four cases. So you can clearly see that. So nature of feedback is a negative feedback, and negative feedback is usually a stable feedback. Virtual short. So we know that in the negative feedback configuration, when the input is being fed especially to the inverting terminal, and the non-inverting terminal is grounded, sorry. So these two terminals are effectively sitting at the same potential. This primarily happens due to the fact that the gain is very high for this op amp, among other reasons. This is one of the more primary reasons, and the input impedance we also take it to be very high. So what that means is that the inverting terminal also is sitting at ground, is at 0 volts. However, no current can flow. That's the term virtual. Short means they are the same potential. And why virtual? Because it's not that physically connected. This means no current can flow through this op amp. So this is an important property, and we'll exploit that in our discussion. So this is the first option. I'll apply a V in over here, and this is the V out, and I simply, so remember, virtual short. So I'll simply assume that a current I is flowing over here. This is resistor R1, this is R2. So if I apply KCL, so current flowing in would be V in. By the way, no current will flow into the op amp because we have assumed infinite input impedance. So the current flowing through this resistor would be V in minus 0 over R1. This should be the same as current flowing through the R2 resistor, which would be 0 minus V out over R2. If you simplify it, we'll get V out over V in equal to minus R2 over R1. This means that for all values of V in, you'll get a V out. There's no specific restriction that is imposed when V in is negative. So this will operate for V in less than 0 and V in greater than 0 and V in less than 0. So this will operate for all V ins. Right, now let's come to this second circuit. Again, this is the input and we have the output over here, and again the virtual short condition persists. So this is this node, the inverting terminal, is again sitting at 0 potential. This problem uses a Zener diode, sorry. So this is a symbol for a Zener diode as it's given. Now Zener diode, so again this is P and this is N, and this is how the output characteristics of a Zener diode looks like. So in the first quadrant, it behaves like a normal, the PN junction. In the reverse bias, very small amount of current flows. However, at certain voltage, and this is usually VZ, which is in this case 5.1 volts, huge amount of current can flow. And the key thing about is that even if the device breaks down, even the Zener diode breaks down, if you again forward bias it after some time, then it will behave like as if the breakdown doesn't happen. This means the breakdown is reversible, right? So what effectively this means is that even for negative bias, if you cross VZ, this diode can sustain huge amounts of current, a few milliamps of current. It can easily sustain. By the way, this reverse saturation leakage is maybe nanoamps or something, or even lesser, right? So Zener diode can function in first quadrant as well as this. It can support large amounts of current in first quadrant as well as third quadrant. So now we'll try to analyze this problem. So we'll take, for option B, we'll take case 1 when V in is positive. So what will happen there? If V in is positive, note this is ground, so current will flow in this direction, Ohm's law, right? And no current can flow in because we have assumed ideal op amp, so infinite input resistance. So that current will flow here. And this makes sense. Note that since V in is positive, right, and this is an inverting amplifier, so what that would mean, this mean V out should be less than 0, and we saw an illustration over here, right? So V out will be less than 0, so clearly this would mean that diode will be forward biased. How do we see forward bias? Because node P, P junction is the P side is connected to 0, N side is connected to a negative terminal. Diode will be forward bias. This means first quadrant, and current can flow. Current can flow. A few milliamps of current can easily flow. So V in greater than positive, no problem. Now let's consider the second case, which I am denoting using the purple color. So case 2, when V in is less than 0, and again this will imply for due to the inverting nature of this amplifier that V out has to be greater than 0. So now V out, so in this case, for case 2, the current will flow in this direction. Ohm's law, this is 0 and this is negative, so current will flow in this direction. Consequently, current will flow in this direction. Now again you can see that diode is reverse biased. Why? Because the P side is connected to 0 while N side is connected to a higher potential. So in this case, diode is reverse biased. Diode is reverse biased, but since its breakdown voltage is low enough, note that the saturation voltage plus minus 15. So in case we are able to breach the breakdown, this means we are operating somewhere over here, right? Again, huge amounts of current can flow. So again, we can say that current can flow. This implies that either that even if V in is negative, some amount of current can flow provided we have breached the Zener breakdown voltage. So B looks promising in that aspect, right? Now we'll go to the third circuit, and in this case again this is V in, the virtual short condition remains, this is V out, and this is normal diode. So what do we mean by normal diode? So this is the first quadrant will look like this, while the third quadrant will look something like this. This breakdown, by the way, will be tens of or even hundreds of volts, right? So this is clearly much after the saturation voltage of the op amp. So again, let's do case 1 when V in is positive. So when V in is positive, and since this is an inverting since the input is through the inverting terminal, so output will naturally be less than 0. So you see this is, and by the way, current will flow in this direction because this is high, this is positive potential, this is 0, so current will flow here. No current can flow inside the op amp, so all the current will flow here. So you can see P terminal is connected to 0 volts while N terminal is connected to some negative V out. This implies diode is forward bias, and since diode is forward bias, current can flow. So current can flow just like in the case of Zener diode. So first quadrant performance remains the same. It would be interesting to see what happens in case of third quadrant. So this is the case 2 when V in is less than 0. This would mean due to the inverting nature, V out will be positive, and you can see if V in is negative, this means current will flow here in this resistor, and correspondingly to according to KCL, current will flow in this direction. Current should flow in this direction, right? So now we can see the P terminal is connected to 0. This is virtual ground, while N terminal is connected to a high, greater than 0 voltage. This means now diode is reverse bias because N is at a higher potential as compared to P. So diode is reverse bias. Reverse bias means it is operating somewhere in this region, right? Because usually the breakdown voltages are very high. So, and note that this current is very low, nanoamps or something. So this means, and we can neglect these currents, this is very small, so current does not flow. Current does not flow means this path does not exist. So if this path does not exist, current cannot flow even here. So we can see that in case of, in this diode configuration, when the feedback is a diode, then no current can flow for negative V in. Now let's also evaluate the fourth option. We have the V in here. This is again virtual short. This is V out. So case 1 would be, so let's see D1 and this is D2, right? So case 1, when V in is positive, what's going to happen? Due to the inverting nature, V out will be less than 0. Now, since this is positive, so current will flow in this direction in this op amp. No current can flow here, so current has to flow between this feedback circuit between D1 and D2 somehow, right? So let's try to evaluate D1. So D1, P side is connected to 0, while N side is connected to negative. Note V out is less than 0, right? So we can say that D1 is forward bias. If D1 is forward bias, this means it's operating in the first quadrant, so can conduct. D1 can conduct, right? D1 can conduct. What about D2? Look at D2. D2, its P terminal is connected to a negative voltage, V out is less than 0, while N terminal is connected to 0. So D2 is reverse bias. If it's reverse bias, and since usually the breakdowns are very high, much higher than saturation voltage, this implies it's operating in the third quadrant, so current can't flow. So what's going to happen is that, so current will flow through D1 and no current will flow through D2. So current will start from V in, and then it will go like this, and then it will drain in V out. So we have seen that. So for positive cycle, this will conduct. Let's check the case what happens when V in is less than 0. Since V in is less than 0, due to the inverting nature, V out will be greater than 0. So the current will be flowing, by the way, in this direction, because Ohm's law 0 and this is negative voltage, so current will be flowing this direction in resistor. Now let's see which one of these diodes is conducting. So let's evaluate D1 first. So look at D1. So its P side is connected to 0. So D1's P side is connected to 0 and N side is connected to a positive voltage. In this case, V out is positive. This means D2 is reverse bias, because its P side is 0, N side is to some positive voltage. D1 is reverse bias. This means it's operating somewhere over in the third quadrant, and it means it can't conduct, and it has not broken down yet, so it cannot conduct. Now let's talk about D2. Now D2, its N terminal is connected to 0, while P terminal is connected to some positive V out, right? So this means D2 is forward bias, and this means operating in the first quadrant, and it can conduct. So what will happen is that the current that is flowing through here, this has to come through D2 like this. So we can see that for the positive cycle, D1 will conduct, for negative cycle D2 will conduct, and so this whole circuit as a whole will conduct for V in positive as well as negative. Okay, so we have seen that D1 conducted without any problems for both cycles, so D1 was good. D2 was good because Zener also connected first and third quadrant. This was good. This was also good because for positive D1 was conducting, for negative D2 was conducting. However, for this is a problem, because when V in was negative, we saw that this circuit was not conducting, and we are required to find does not operate. So C is our correct option. Thank you for listening.